Hi, so my name is Areej Ilyas, and I'm a master's student from IBA Karachi, Pakistan. And this is something that I've been working on for my master's thesis, which is ongoing. So the topic of today's talk is non-locality distillation with non-trivial marginals. So we'll jump right into it. Let's consider two parties which are separated spatially from each other. So that means they are not in the same room, or they're not non-local to each other. They share some kind of joint behavior at their ends, and there are certain inputs and outputs like X and Y on each end, and they get it outputs A and B. So these outputs are correlated. We consider the correlations which can be produced without any communication between these two parties. And we don't have to consider the underlying apparatus for physical apparatus for this system. We just look at the joint probabilities between the outputs conditioned on the inputs. So these correlations are non-local when they cannot be explained by local shared randomness. There are strong non-local correlations that are used as an information theoretic resource. For example, the security for the QKD protocol, that is the quantum key distribution protocol. As the non-local correlations become stronger, the security for the QKD protocol also increases. So that is why we can use these non-local correlations to understand and enhance our knowledge of the quantum theory itself. In this work, we have considered the amplification of weak non-local correlations via distillation protocols. There are stronger than quantum correlations that are known to be unnatural because they cannot be explained by classical or quantum mechanics, but they have been studied extensively under the information theoretic principles such as trivial communication complexity, because they make it the communication complexity trivial. So one of our motivations for considering the non-locality distillation was to discard these stronger than low quantum correlations, and distill some weaker correlations to a higher degree of locality. There are distillation protocols that have enhanced non-locality, like there is a non-adaptive distillation protocol with trivial marginals that is known to be optimal, that is the PARITY protocol. We have found that the OR protocol performs better non-locality distillation with non-trivial marginals than the PARITY protocol. So now let's consider a game where these two parties, such as we can call them Alice and Bob, are in two separate rooms and are non-local to each other. So we call a system local when it's explainable by local shared randomness. So there's this inequality known as Clauser-Horn-Shimony-Hall inequality, which is one of the first example of this non-local game. We use this inequality as the measure for non-locality. So we can calculate this value by adding all the winning probabilities of the game and subtract all the losing probabilities from it. So the winning condition for this game would be that whenever the logical AND of the input bits that are X and Y are equal to the parity of the output bits, then we are winning the game, otherwise we're losing. So we can define the classical quantum and no signaling region by these values. Whenever the value CHSH inequality value, we're using V for that, is less than or equal to 2, the region that is the correlations are local. And then if the value goes beyond 2 and is less than 2 under root 2, we say that the system is quantum, the correlations are quantum and can be explained by quantum mechanics. But if it goes beyond that, then we go into the region that is the no signaling region, which is between 2 under root 2 and less than 4. So these are the unnatural correlations that we talked about. So at value 4, we have the perfect box known as the PR box. There are certain restrictions on these probabilities. So first is that all the probabilities should be positive. The second is that the probabilities, sum of all the probabilities should be equal to 1. And the third is the no signaling constraint, in which Alice's input and output has no effect on Bob's input and output, and vice versa. So that just means that the sum of Bob's joint probability distribution is equal to Alice's marginal distribution. So now let's take a look at the PR box. We're just considering this box as a black box, and we're just looking at the input and looking at the output probabilities conditioned on their inputs. So Alice's half gets some input here, and Bob's half gets some input on his end, and we get A and B as output on both of their ends. So we can describe this box by the following probability distribution, where the winning condition of the game, whenever this is satisfied, we get a half probability, otherwise we get 0. So if we take a closer look here, whenever the input for Alice and Bob is 0, 0, 0, 1, or 1, 0, we get the same output bits on both ends. So whether it could be 0 or 1. So both of these conditions happening with a half probability. And when they get input, both of these parties get input as 1, the probabilities are opposite. So either Alice would get 0 and Bob would get 1, or vice versa. So this is the winning probability for this case. So this is the box that is known as the perfect non-local box. And when we calculate the CHSH value for this box, we get the winning probabilities and subtract the losing probabilities, we get the value 4. And whenever this value is less than 4, that means there is some kind of error in it. And we define or represent this error by a bias. So these are the values, delta 1, delta 2, delta 3, and epsilon, that we're using as bias values, and we're showing this correlation for a box that has some kind of error in it. And when we calculate the value for the CHSH, we get this following equation here, delta 1 plus delta 2 plus delta 3 minus epsilon. So if we take a closer look at the decomposed probability, we see that this is how we define it. These are the local marginals, which we have kept trivial for now. So for each row, there is a bias. So if we take a look at this probability, we all A, B, X, Y are 0. So we get 1 plus delta 1. The positive sign comes from the output bits parity of the output bits. So we get 1 here, and this becomes positive. And the value that for the row was delta 1. So this is how we can construct this box. There's another box known as the non-local box with non-trivial marginals. So you can see this box is the same as the one that we saw earlier, but there is something extra here, that is A, B, C, D values. These are the local marginals, and we can use this as a resource for non-locality distillation. But when we calculate the CHSH value, we see that it's the same that we saw in the earlier box, which means that it is independent of the local marginal. The value of CHSH box or a single box is independent of the local marginals. So if we look at these, another example where we have local marginals as well, we take the same example, 0, 0, 0, 0, we get A and C as the local marginals here, which are the delta 1 is the same that we got earlier. A is because Alice's input was 0, so the local marginal is here, and when Bob's input is 0, we get C as the local marginal. So we can construct this box the same way. Now let's take
So we have.
Hello. I think that I got disconnected. Am I audible? Hi. Can you see me?
Yes, it's okay. So can you share your screen?
Okay. Where did I lose you guys? I just want to know that.
Maybe 1 minute ago.
So were we somewhere? Where were we?
Yes. No, it was the next one slide.
So this wasn't this here?
Yes, here.
Okay. Apologies, I don't know, I got disconnected. So I'll start from this slide again. Okay, so when we're talking about the distillation concept, I'm audible, right?
Sorry?
Am I audible? It's clear, there's no distortion.
So everything is okay right now.
Okay, okay, great. I'll just continue from here. So, so the concept of distillation I was talking about is that whenever we take a pure form from an impure mixture and extract that from it, we call that concept distillation. So we use this concept here where we take multiple copies of weak non-local system and amplify the non-locality using the multiple copies, and with a given correlation with a certain non-locality, we can use multiple copies of that given correlation and turn it into a new correlation with a higher degree of non-locality. Using this concept here, we have multiple copies of non-local boxes here, and they have certain CHSH value for them. And when we use these boxes together to create a new box with certain inputs and outputs, which can distill to a higher value. So this is known as the non-locality distillation. And Alice and Bob can wire these boxes in using classical circuitry to produce new binary outputs and inputs for this box. So these when we apply the Boolean functions to the output bits here, we get the final bit that is for the new box. So this is known as, we're calling this as protocol. And if you must have noticed looking at this picture, we have different output bits, but we do have the same input bit for all the boxes. So this particular example is known as the non-adaptive distillation protocol, where the inputs are the same in all the identical boxes, but the output bits are, but where for adaptive protocol, we have the second box has the input dependent on the output of the first box. So, but we are concerned with the non-adaptive distillation protocol, so we will be looking at that. As discussed earlier, parity protocol is optimal among non-adaptive distillation protocols with trivial marginals, and we are looking at non-adaptive distillation protocol with non-trivial marginals. So from our numerical analysis, it was found that the OR protocol performed better non-locality distillation than parity. So that just means that the Boolean function that was applied to the output bits was the OR protocol. So if we apply certain restrictions to the box, the non-trivial box that we had earlier, we keep all the non-trivial marginals to be equal and the deltas to be equal to 1. We can define the following box with this correlation and call it correlated non-trivial box. And we can get the CHSH value for this box as well by adding all the winning probabilities and subtracting the losing probabilities from it. So we can also get the parity protocol value and the OR protocol value using the same equation. So to determine where the OR protocol performs better than parity, we solve this equation inequality where we say the OR protocol is greater than the maximum of the parity protocol CHSH value and the single box value. We get this following equation, which whenever is less than 0, it gives us a higher value for the OR protocol than both of these values. So if we take all the non-local marginals equal to A, and are between 1/4 and 1/2, and the bias is 1, delta is 1, and epsilon is between 1 minus 4a and 4a/3 minus 1/3. This equation is always negative, which means the VR protocol is distilling to a higher value. So if we take this as an example where we keep delta equal to 1 and non-trivial marginal to half, we see that the OR protocol, this is the red line, which is the OR protocol, is distilling a higher value than that of a single box, that's a black line, and parity, which is the blue line. So we can also see that whenever this is the same region for which the equation is negative. So for the whole region, this is distilling a higher value. But when we looked further into the epsilon and delta values, we saw that whenever the value fell below 2a minus 1, the box became signaling due to the positivity constraint being violated. If you remember the no signaling polytope slide where we mentioned that the positivity constraint, where it said that it should be, the probability should be positive. So here it becomes negative. That's why it's no longer a valid box. So for OR protocol to distill a higher value than that of a single box and that of a parity protocol, the box and the box be non-signaling, the epsilon range is then modified by the following value. Here we take the lower bound, which was this was the earlier lower bound that we had, and now with the maximum of both of these lower bounds, we get the new lower bound that is for the epsilon value, and the rest is the same. So for this, we can say that the OR protocol is optimal protocol. for this section. And if we take the same example that we had earlier, where A was equals to 1/2, we can see that the original value when we substituted in 1 minus 4A, we get -1, which was here. But when we put this value in the positivity constraints lower bound, we get the value 0. For this case, the lower bound becomes 0. And this is the region where the OR protocol is distilling a higher value, and the box is non-signaling as well. But there are cases where this original bound is the maximum value, and the whole region is distilling to a higher value, and it's with the non-signaling box. So if we remove those restrictions from the deltas equal to 1, we have another box that we call symmetric non-trivial box, and that's just the same box as the correlated non-trivial box, but we just have the deltas that are variable now. Using this box, we can generate another equation which says whenever is less than 0, we have your protocol distilling to a higher value. And same for further increasing the search space, we can take two non-trivial marginals and get the following expression where A and B are the capital A and B are the marginals here, and this equation whenever is less than 0 gives us a higher distillation value for the OR protocol. So if we take a look here in this table, as we go along increasing the non-trivial marginals, we see that the OR protocol is distilling to a higher value when we've kept the deltas and epsilons the same, and showing us that the single box and parity protocol values are not changing, and they are independent of the non-trivial marginal, and also the effect of the non-trivial marginal on the values of the OR protocol as they are increasing. So for future work, we can look into a complete characterization of these optimal protocols, be it adaptive or non-adaptive, for general non-local boxes, and its application, the application of non-locality distillation to the information theoretic principles such as the trivial communication complexity. And we can use the OR protocol to see if it increases the region for the communication where the communication complexity is trivial. So that's it from my end. Thank you so much.
So thank you very much for the nice talk. Thank you. We have no questions in the chat. Maybe someone can ask. No. So great topic. We have an only comment. So we have great topic. We have a nice presentation. So thank you so much. And
thank you so much.
Thank you.